All right, so we are now recording. Share the screen. Okay. All right, so we're going to continue our discussion. Just to kind of wrap up the previous topic, right? Again, I provided in these set of slides several models, and I'm just trying to provide contrast, right? So it might be helpful for you guys to understand, okay? So basically here, there are several, again, it's progressing in that direction, right? From in this direction. And it's basically all the different architectures that we can build. So we start at the perceptron, which is, as I said, the 1940s. Then we've got the linear regression, which is actually what you guys did. Then we've got logistic regression, which is the one I've discussed today, which is not a neural net, but it is a classifier. And then we've got the multi-layer perceptron, which you guys should be very familiar with. We've used it a lot this semester. And then deep learning, okay? So I'm contrasting these 5 models, basically, where the perceptron would be the original idea of a neural net and neurons and things like that, okay? So basically, what I have in here in red is the inference part, and what I have in blue is the loss part. So the 2 functions again, right? So for the perceptron, it just uses a simpler update because it was the first idea, right? That's the optimization. Again, I'm not going to cover perceptron. That's more like the foundations class if you are interested in that kind of thing. All right. But that was the original idea. So we kind of pick up here, basically, where we actually use these models in a more applied way. The optimization here, as you are now very familiar, is MSE or LSE, however you want to call it, same idea. Then we have logistic regression. So remember, regression is for continuous values, so you should know this, right? You know, like the wine data or temperatures, it's 32, 36, 37. And then these 3 over here are for classification, right? So classes. So we've got that all 3 basically use cross entropy, which we have already discussed in the previous discussion, all right? And then that's the optimization function. So this is the same for all. Like if it's logistic regression, which is not a neural net, it's cross entropy. If it's multi-layer perceptron, cross entropy. If it's deep learning, it's cross entropy. Doesn't change, right? So for classification, that's going to be. What changes is the inference function, right? So it's nice to think of the inference function. Notice that the perceptron also looked already. It was the same idea, right? A multiplication of weights times a multiplication of the x input. The regression is just that, right? Which should be familiar to you. Just think of these as vectors. So these could be multiple x's, multiple w's. I'm just using this as a vector, not as individual variable. The logistic regression, notice, is basically the same, but now we have this z value. It's a logit, and it goes through a function which we've already defined as sigmoid, all right? It goes from 0 to 1. The multi-layer perceptron, now notice that the thing is now you've got W1x plus B, and that produces C1. So that's the input to the function, which produces H1. And then notice in the next layer, it's W times H1, the previous one, plus, so it's W2, B2, it gives you Z2. And then Z2 goes into an F, and that produces the Y. So this is how I have introduced a hidden layer. One hidden layer. So this is the architecture for the multi-layer perceptron in functions notation. If I want deep learning, same idea. W1 x plus B1. Notice the x is the input, goes into C1. C1 goes through an activation, then you get H1. H1 becomes the input to the next equation, right? W2, which gives you C2, goes into another activation, and then ... So this can go on for a while until we get to H n minus 1, and that's the input for Zn, which then would go through an activation, which could be softmax, for instance. Is this clear, guys? This is the function representation of what we're doing in code, right? So the neural networks. Yeah, okay. Now, on the exam, I could give you this and ask you for the diagrams, or I could give you the diagrams and ask you for this, okay? So I provided here an example of how that would work. So I have here the 5 examples of functions, and then down here, I have the 5 examples of the diagrams themselves, okay?
Or if you want us to make it some other.
Lenny, however you can make them is fine.
Okay, so I'm not very good with my handwriting.
Oh yeah, if you don't, yeah, I mean, I would just draw it by hand, take a picture and put it in, but you can draw it with a tool. Yes. Yep. Any questions, guys? Other ones? All right, so let's think about the architecture, right? So the perceptron, basically, as far as the diagram, looks like this, okay? Linear regression, this one, so we're skipping perceptron because we're not really covering it in this class, but look at linear regression. It's basically an input vector and an output vector, right? No activations, as you guys can see, and it just looks like this. Okay, this is the inference function. This is the diagram. That's why we call these things architectures, right? Because you guys are building these layers and defining it, so it's right. So we obviously don't do it like that. We code it, but they're neural nets because they look like that. Okay. All right. So now I should say I was they're not all of them are actual neural networks, right? To be a neural network, 2 conditions must be met, which are you have to have at least one hidden layer, and there's got to be an activation function. If you do not have that, like if you have an input, a hidden layer, and an output, but no activation, it's still a linear function. And so it can't create like the curve that we talked about to separate the data. It's still just a line, okay? Straight line. Does that make sense? Okay. All right, so logistic regression, notice basically it's got the input vector, just like linear regression, but notice there's a difference. The output is going through a function. Which function? The sigmoid that we just looked at. You remember it, the 1 divided by 1 plus e to the minus z, right? That's the sigmoid. Now here, the architecture can be like this format or like this format. Remember, this format down here is called a one-hot encoded format. Okay, got it? Does this make sense? All right. Notice this has an activation, but no hidden layer. So is it a neural network?
No.
No. Very good. Yeah, excellent. So you have to meet both conditions, okay? So here we have one, multi-layer perceptron or MLB. That was this function up here. Notice how I added that H1 hidden 1. It creates that layer. So now if you look at it here, I have 1 input, 1 output. There is an activation here, which is softmax, which we have already discussed. But now I'm throwing this hidden layer. Without that activation, it would still be linear. If I add the activation, now it's got the 2 requirements to be a function that can approximate, curves, nonlinear solutions. Okay. And so that basically here, ReLU has been selected. Okay. And then deep learning, of course, you have inputs, outputs, and then multiple hidden layers where the hidden layers have activations. And basically it looks kind of like this representation. Yeah, Lenny.
The inference functions are when the y equal to something. So if y equals w, and then does each one have a inference function? So the multi-layer perceptron function is y equals f. And
That is a good question, right? So the inference function of the multi-layer perceptron is all of this that is red here.
okay.
Because how do you know where the input is? X is the input, right?
Yes.
So that goes in first to this equation, which produces a C1. C1 goes through an activation, F, could be ReLU, sigmoid, etc., and produces H1. And then H1 is now the hidden layer. And that hidden layer then goes into another connection to the output. So if you notice here, I have to create another set of weights, another set of biases, and that gives me C2, and C2 goes into F, the activation, to produce Y.
Okay.
Hmm?
Thank you.
Did I not say it right? C2 goes into F, right?
Yeah, these two.
But it's not activation.
It's a softmax. Softmax is a type of if it meets the same criteria. It's like sigmoid, but it only adds up to 1. So it's actually, guys, any activation just means it changes the data from one thing to another. Does that make sense, guys? All right, so the red is the inference, the blue is the loss functions, and then here I've drawn the diagram, which is a kind of thing I like to ask questions about on the exam. Okay? And that's why they're, and don't, so that's the idea. All right. We've talked about softmax, so that's why I'm not going to talk about it today, but I did provide here a few activation function examples, just so that you, and again, in a contrast fashion, so it makes a little bit more sense. So for those of you that, are from electrical, you've heard of step functions, so it's 0 or a 1, and that's why it's a step, right? So if you notice, it looks like a step. So when the value, again, the inputs are in the x-axis and the outputs are in the y-axis, so it's either 0 or a 1, a step function, okay? Sigmoid, we've already discussed, and I showed you the curve, right? Tan H, which I think you may have seen me use it, is almost like sigmoid, except that instead of producing values between 0 and 1, it produces values between -1 and +1. That's it. Got it? That's it. We're just mapping our values from one to the other. Softmax, like sigmoid, but values add up to 1. I've shown you even a Python example last week. And then there's ReLU and GeLU. So I don't have the GeLU one. The G stands for Gaussian. So it considers Gaussian properties. ReLU, I did provide that one here. And that one is called sometimes the hockey stick shape. Basically what it means is if the value, so remember X and Y again, right? The inputs are X, the outputs are Y. So if the values are negative, it makes them 0. Okay. If the values are positive, it keeps them as is. That's why you notice this is just a line going up. So if this is 2, this is 2. 3 is 3. But if it's negative, it becomes a 0. And that's what ReLU does. And ReLU has been shown to be pretty good. Okay, pretty good. Got it, guys? Make sense? So these are the activation functions. Okay. We've talked about one-hot encoding. Yeah, and then this is just a linear regression optimization function. So this is kind of like an intuition of what MSE is doing, okay? So if you notice, you got some red data here, right? And you're trying to fit a line to it, okay? So maybe the best way to understand about minimizing the error is to think of 2 curves. Although you could have an infinite number of lines, straight lines in this space. But I'm just going to look at 2 possibilities. How do you come up with these 2 lines, which are this blue line and this blue line? Because you've selected different parameters, different weights and biases, okay? So when you have a set of W's and B's, you get this blue line, call it B. And when you get another set of weights and biases, you get this other blue line, A. Now, what do? For each line, you calculate the difference between the actual data point and what the line marks for that value. So for instance, if X is this one, right? And I come here. So that means on the line, it's this point here, right? But the real value, the red one, is this one. So the difference between them is just this. Do you see that? Now you do this for all the points in relation to that line. You sum those differences, right? And that's your error. You guys see that? Now let's look at the other case. I have the red dots don't change, right? Because that's the real data. But I have now another set of weights and biases, and that produces this blue line over here. Do you see that? So now the differences have to be with relation to the red dots and this blue line. So again, I'm going to take the same X, right? Which is this one over here is the red dot. But now the predicted has to live on this line. So the difference is all of this. And you calculate for all points this difference, and you take the sum of them. So obviously, which one will be better, A or B? B. Why? Because it minimizes the errors. Do you guys understand? This is MSC and what it's doing in graphical form. It's always calculating, picks an X, and it goes like straight, right? Perpendicular to the X-axis. And so it just looks at the red dot and whatever that is on the line that you have. So you're going to pick the line that out of all the points will have the lowest distances, the minimization. That's why it's called the minimization, which is denoted by this equation. Got it? Any questions on this idea? All right. So that's that. And then I think we've mentioned all of this. Yeah, so we've talked about this for linear regression. I've talked already about this for cross entropy, so I don't think there's anything new here. And this was, we've already talked about this, I believe. What is that curve? It's basically for a neural network, what the loss function looks like, right? The actual one. So the idea here is that you have the W's here and you have the cost over here. And it's like a combination of all the losses from cross entropy, right? That actually, if you look at the whole loss landscape, it would look like that. So unfortunately, because there's so many, it's like when I gave you cross entropy, it was like one mountain and one valley. But actually, when you look at a whole deep neural network, it's like a whole bunch of mountains and valleys, and it creates a whole range of them. So although if you only had one, you would achieve the optimal, right? The problem is you have many of those, and some are higher than others in the landscape. So it creates this example here where there's some local minima and then there's a global minimum. There is one, if you fall here and you keep navigating, you get to this point. And that is the absolute lowest for that mountain range, if you will. Okay? And that's what it is. So even though we're using cross entropy, think of it as there's a lot of cross entropies that for each individual case. And so we got to balance out all of them, right? Not just one. Make sense? So this is why you always get a graph that looks like this when people are describing the loss function for deep learning. Okay, and they are always going to say there's global optimum and local optimum. So that's why sometimes you select some weights and your performance just doesn't improve. It's because you get stuck here. But if you are lucky and you start weights here, you know, gradient descent will get you down here. Obviously, it's much more complex than this graph. Okay? Got it? All right. Anyway, so as I said, the best way to understand this is to take cross entropy, which was one set of curves, and now imagine it's multiplied and multiple options. Okay? All right, so that concludes. So this is what I wanted to do before the exam. This was kind of a review of a lot of the topics that we have covered in code. but more like the theoretical framework of it, okay? All right, this concludes this part, so are there any questions on this? No questions? All right, so I'm gonna go back to the video and I'm gonna create a new separate video because this is gonna be CNNs now. And so I kind of want to separate these out. Oh, I'll do it up here. All right, so I'm gonna, if I stop.